remember the place. But what I wanted to do actually was show you some of the equipment that we're going to use when we go out on the field to the Carrabassett stream. This one's pretty straightforward. It's a piece of concrete that's been tied to a rope, and we'll use that particular instrument to drop it off a bridge while we're holding on to the other end, and we'll be able to measure the depth. The black marks are in tenths of meters and the red marks are in half a meters. And then we have a tape measure here. The tape measure allows us to measure the width of the bridge, etc. Then we have a couple of other bits of equipment here. This is going to be used for the velocity measure. This is the actual propeller that will stick into the water. We'll come back to that in a minute. And we can measure up in tenths of meters. And you see it's fairly long. And I didn't screw the end of it on because it's a lot easier to put in my car when it's in separate pieces. And then the information from the propeller travels up this wire and travels into this box and goes into this recorder, and it's connected by Bluetooth to this iPad. And if I can get it back up and running, I can show you how it's going. I have to put the password in because I waited too long. Okay, we're back. So it's hooked up and ready to go, and you can see that it's had some time running along here. Ultimately, this is the time when I need 3 hands. But if you look at the graph here, and I spin the propeller, we have to push collect. And now if you look, when I spin the propeller, you can actually see that a line is being generated, and then we can save that, and it'll give us the velocity of the stream at whatever depth that we put it in. So that's a little bit prep on the equipment. Now I'm going to go out and get in the car, and we're going to drive out and do the field trip. So I'll see you in a few minutes. Good afternoon, and welcome to the Carrabassett stream. We're located about 15 miles from the Colby campus, and we usually come here on a bus, but you can watch this field trip and complete the exercise in the comfort of your living room, your study, your bedroom, wherever you happen to be doing this. Geologists have always looked at streams because streams have a variety of different capacities that they perform geologic work. Probably the one that's most easy to recognize is the fact that streams move sediment. But that's not the only reason that geologists are concerned and interested in looking at streams. One of the other things that we're concerned about is the fact that it produces energy. Water going over a falls makes energy. That produces power. We can use that to run a mill. We can use it to generate electricity. We can use it for a variety of different things. What we're going to do today is we're going to actually calculate and measure the amount of water that flows underneath this bridge in a given amount of time. And what that measurement is called is discharge, and we use the letter Q to calculate discharge. Now, you should be a little bit familiar with discharge because it's just the volume of water that goes by a given point in a given amount of time. You did that when you calculated permeability. Permeability is just the amount of water that flows through a sediment in a given amount of time. So you did that when we did that laboratory that looked at porosity, permeability, and grain size. So we're going to look at a little bit bigger body today. We're going to look at the Carrabassett stream. And the Carrabassett stream is a small tributary. It flows from Oak Pond up in Skowhegan, and it flows through Canaan and Clinton and ends up in the Kennebec River, just about where the bridge, the big bridge goes over in Fairfield. So we have to take 3 measurements today during the course of our exercise. We got to measure the width of the stream, and basically we'll just put a tape measure over on that side of the stream. We'll measure over to that side of the stream using the tape measure. Our measurements will be in meters. So what we'll do is we'll figure out maybe it's 15 meters, maybe it's 16 meters across, and we'll leave the tape measure there between the guardrail and the bridge abutment, And what we'll do is every meter, like 1 meter, 2 meter, 3 meter, we'll go across and we'll actually take a big rock attached to a rope and we'll measure the depth. And what we'll do then is take that depth, all those depth measurements, be it 15, 16, 20, we'll add them all up and divide by the total number of measurements that we took, and we'll use that as our average velocity. So we have two measurements, the width and the depth, and now we need to calculate the velocity. And if you look at the stream today, we can zoom in a little bit at the water, you'll see that the water is actually moving at a pretty good clip. You can see the current, and it looks like to me the water is coming at me. And if we go across, we can see that the water's actually coming out underneath the bridge and flowing away from me on this side. So if we look at the geography, north is that way, okay, north is that way, and south is this way. So the stream flows pretty much from north to south. So there's a real simple way we could do this. We could take a stick and throw it in the water and time how long it takes the water to go from underneath the bridge to the other side. Then we could measure it, and then we'd have distance over time, and we could calculate the rate. But what we found out is that the average velocity of the stream, which is what we actually need, is not on the surface. Usually when I come out here and I ask students, what do you think, where do you think the stream is the fastest? Most everyone says at the surface. And there's a little problem in there. It's not exactly at the surface. We have a little problem in that there's friction between the air and the atmosphere, and maybe even the wind. You might be able to hear it today, though it's not too bad. The wind and the water, and that actually causes the surface velocity to slow down. So then people immediately will say, oh, then it's at the bottom. And it's not really at the bottom either, because there's even more friction at the bottom, because there's friction between the bed of the stream, and there's friction between the water and the bed of the stream. So what we have to do is figure out where then would we measure to get the average velocity. And what geologists have found over time is that if we take a depth measurement and we come up 6/10 the distance from the bottom, it was a very easy calculation. Say right here at this point, we measured 2 meters. We'd multiply 2 meters by 0.6, and we would get 1.2. So consequently, what we would do is we would take our velocity gauge and go down into the water. And what we would do there is hold it for a minute, see how many revolutions that the propeller spins, and then we'd hook it up with a little device that we have that actually draws a graph and run it for a minute, and it would give us the average velocity of the stream. What we should do is, if we measured 20 measurements, we should do the average velocity at 20 different depths. We don't have the time to do that today. Normally we're under a time constraint to be back by 4 o'clock. Today I have all day, but you probably don't want to sit and watch me measure 20 times. So what we're going to do is measure one time. We'll take that as the average velocity of the stream, and we'll have the three elements that we need. The width of the stream, which is W, the average depth of the stream, which is D, and then we'll have the average velocity of the stream, which is V, and we multiply those three units together, width times depth times time, our velocity, and we get discharge. And we measure the discharge in meters of width, meters of depth, and meters per second of velocity. So if we multiply those three units together, we would get cubic meters per second. Now, in the United States, we're one of the only countries that doesn't use the metric system, so we typically measure discharge in cubic feet per second. And there's 35 cubic feet in a cubic meter. So if we had cubic meters per second as our discharge, we could multiply the value that we got for discharge in cubic meters per second by 35, and we would get cubic feet per second. And I think that pretty much takes us to the point where we actually would measure the stream and do the calculations. All right, some information that we need to sort of think about that we brought back from the field. When we measure the average velocity, what we're going to do here is use the 6/10 rule. And I think when I was measuring in field, I used the wrong measurement. What I said was 6/10 of the distance from the bottom, but what we should measure is 6/10 the distance from the surface of the stream. So in this particular example, what we're looking at here is a stream that has a width of 21 feet. And we measured it every foot going across, so we have 21 measurements. We have a maximum depth of 7.5, and we have added all those up, divided by 20, and came up with a depth of 5.23 feet. Our average width is 21 feet, and to figure out where we're going to measure the velocity, we take our maximum depth, which is 7.5 feet, multiply it by 0.6, so we would come down at 4.5 feet, and that's where we measure the velocity. And arbitrarily we're going to say that the velocity in this particular stream came out to be 2.5. So we plug those into the formula where Q, which is the discharge, equals the width times the depth times the velocity, and we plug the numbers in. The width is 21 feet, the depth is 5.23 feet, and the velocity is 2.5 feet per second, and we come up with 274.6 cubic feet per second, or if we convert it to cubic meters per second by dividing the number that we got in cubic feet by 35, we get 7.8 cubic meters per second. So there you have better explanation than I did out in the field, and that should work for what we need to do. Okay, so we got some live science going on here at the Carrabassett stream. My two colleagues, Laura and Manny, they're dropping the weight down in and measuring what the depths are. What we're going to do is add these cumulatively and come up with an average depth for the stream. You can see in here we have the tape measure set up between the bridge structure and the guardrail, and we're actually going to lower the weighted measure down into the water at every meter going across here. And what we found was the width of the stream is 14.9 meters. Right now we're about halfway across the stream. We're saving you an awful lot of time of watching the excitement of science.
What would you say this is? Oh, it's kind of going. Start playing.
Sure, I can always crop it. All right, first thing, like, hey kids, don't do this at your house.
Hey kids, don't do this at your house.
All right, can you hold that? Right.